When you're talking about organic chemistry, what you're really talking about is just the type of chemicals, and specifically for us it'll be macromolecules, the big molecules. But we're talking about the type of things that you'd find in living things. So organic meaning that's from living things, as opposed to non-organic, which would be like rocks and soil and stuff like that. Okay. We have to go all the way back to grade 9 and 10. I'm going to go back to talking about the individual elements. Now you would have learned back then how to do these little Lewis dot diagrams. Didn't show up so well on the iPad last time I drew it, but that's okay. So hydrogen, hopefully you remember. Actually, let me grab you a periodic table. So looking here at the periodic table, here we had our little hydrogen sitting over here on the left-hand side. Hydrogen has, if you remember, the atomic number. If it's 1, that means the number of protons. And then this is the atomic mass here. And that's basically the weight of the, or I should say the mass of, because weight depends on gravity, but it's the mass of the actual nucleus itself. Remembering that electrons are so tiny whizzing around the outside that we don't really calculate them into our mass here. They're just too small. But remember that you have the proton and you have the neutron, and that they both are pretty much equally weighted. Neutron is ever so slightly heavier, but we can still treat it as being weighted as 1. So really, if I've got 1 proton, I can see that here, and I weigh 1, then I don't have a neutron. So there is no neutron for hydrogen here. When we go down to lithium, lithium has 3 protons, has a mass of 7. So if 3 of them are protons, the other 4 have to be neutrons, right? Everybody okay with that? Hopefully. Now, we don't care so much about neutrons in this particular case. We don't care about the actual heaviness of our of the atoms. What we care about is how many electrons it needs. So hopefully you remember this from grade 9 and 10, because I know some of you haven't had your grade 11 chemistry or grade 12 chemistry, but last time you had it was 2 years ago in grade 10. So here you've got your hydrogen. Remember that everybody that's in this first column here, whether it's hydrogen or whether it's these alkali metals that are in the first group here, these guys all have 1 electron in their outer shell. Okay? Then you have the next group over here, beryllium and down. That would be 2. Then you skip all these pink transition metals and you go up to boron. Boron would be 3. Carbon has 4, and everybody under it has 4, well, for the most part. 7. When you hit nitrogen, then that would be 5 in the outside, 6 in the outside, 7 in the outside. And then helium is 2, so it's full. And then neon down has 8, so they're full. So these guys are non-reactive on this side. And you got 1 all the way up to 7. So 1, 2, skip a few, 3, 4, 5, 6, 7. That's the number of electrons that you've got in the outside shell. Why do we care about the outside shell? Because they will interact with one another based on how many electrons they still need to steal, or how many electrons they can share, or how many electrons they're going to give up. So this matters. One of the main things that we'll keep talking about is how oxygen and fluorine are sitting way up here in the top right-hand corner of the table. Oxygen is in the human body. Fluorine should not be. Fluorine is the greediest hog for electrons in the entire table. Doesn't mean that it's the most reactive, but it means it's what we call the most electronegative. It's very highly reactive, and it'll try to steal electrons from anybody and everybody. So we actually don't want fluorine in our bodies because it would just be too reactive. Oxygen is the next biggest bad boy, so that if fluorine is the godfather of the table, oxygen is his right-hand man. So oxygen is the big bad boy who's going to try to steal from everybody as well, and is present in the human body. So remember that oxygen is an electron hog. This is why we use the term oxidation, if you've come across that word yet. If you haven't, it's okay, I'm going to explain it. But oxidation is named after the characteristic of what oxygen would do. So if something else oxidizes something, we're like, oh yeah, you're acting like oxygen, because oxygen would steal electrons from things, okay? So oxidizing comes from the idea that oxygen is such a greedy electronegative electron hog. Looking at this table as well, if you're coming up in this direction here towards fluorine as being the most electronegative, so the greatest love and the strongest hold on electrons is over here in the corner, then obviously the weakest hold would be over on the other opposite end. But we would also say, not only do they have high electron affinity over here by fluorine, high electronegativity, but we'd also say they have high electron affinity. Affinity is an attraction or a love for something. So I always give this example. I have a very high affinity for lasagna, and so I love lasagna. So I would say high affinity for lasagna. So fluorine loves its electrons. It has a high affinity for electrons. Okay, so there's our table at a glance. Just keep in mind oxygen and fluorine are over here. Notice nitrogen's right here, carbon's there. Phosphorus and sulfur are also important in the human body. Usually we say it's C, H, O, and N, CHON, C-H-O-N. Those are the most common elements that you have in your body, C-H-O-N, probably in that order as well. And then you've also got, no fluorine, sorry, you've got some phosphorus, you've got some DNA, and you have other trace elements of things. So for example, in the middle of your red blood cells, you've got some iron, you've got manganese in some cases, and some cases, where's chromium? Sometimes you got a little bit of chromium in there. These are trace elements that you would also see within the body as well. But the main elements would be CHON with a smattering of other things. With all that said, here we are now looking at the actual elements themselves individually to see what kind of bonds they can make. So hydrogen had one electron in the outside shell. Because it's in that first period way up at the top, it's just hydrogen and helium in that first top row, that top period. It only needs to have one more electron in order to fill its shell, because it only has one shell. The first shell only fits 2, and then the next shell will fit max of 8, third shell max of 8 up to 18, depending if you're transition metal, etc. So we only need one more. That means it has a bonding capacity of 1, because I can fit one more. Oxygen has 6 electrons in its outside shell, 8 total, but 6 just in the outside. We're just talking valences here. So it has space for 2. I can put 1 here, and I can put 1 there. So we say it has a bonding capacity of 2. Sulfur, 1, 2, 3, 4, 5, 6, same as oxygen. It's right underneath oxygen in the table. So it has space for 2 as well. Nitrogen has 5, so it has space for 3 more. Carbon has space for 4 more. And then phosphorus also has 5, so it has space for 3 more. You need to memorize these bonding capacities because they're going to help you when you do your drawings. Here are just some simple examples. You have water. Oxygen has space for 2, and so you can stick 2 of these hydrogens who each need just one more bond, and then they end up sharing those electrons. So memorize the bondings. It's going to matter. You're going to want to check your work and come back to this. I'm going to explain more about this kind of stuff, again, if and when I can get my iPad talking to my computer. On these big molecules, and again, this is all posted. You guys can copy this later, so don't worry about writing it all down right now, unless you want to copy part down while I'm talking, but don't miss what I'm saying. Let me just zoom out a little bit here. Built into molecules, you have these parts that stick out a little bit. Let me flip pages here. So if you look at this here, this big vitamin B molecule, you can see that there are all these little sticky outy bits all across the entire molecule. And it's these little bits that are sticking out. They're called functional groups because they will determine how this molecule functions, how it works, how it interacts with other molecules. Whatever's sticking out matters. And it matters exactly where it sticks out. Think of these as 3D molecules. So when you're looking at this picture, this is a shorthand form of a diagram like this. This is organic chemistry stuff. What they've neglected to put in, because there's just too many of them, is all the carbons. Every time you see a join, like up here where this oxygen is on the left-hand side, nitrogen and oxygen aren't connected to nothing. They're connected to a carbon that's sitting here. And then every time you see a benz, there's another carbon sitting there, and another carbon, and so on. You've got these carbons that are sitting there, but there's just so many of them. So every time you see a join where there's no letter, it's a carbon. And in fact, what they've even done here is, see how it kind of sticks off into nowhere here? There would be a hydrogen sitting here, because they're just so common that you don't necessarily want to put them all into every picture. It's also meant to be done in 3D. So if you see just a normal line, imagine that it's just being a normal plane, like it's just sitting flat. Whereas if you see a dark line, a dark fat thing like what's attached to this hydrogen, imagine it coming out towards you in 3D. And then with these dashed lines, imagine them going away from you. So that because this thing is dashed here and there's nothing on the end, I know that on this side of the dashed line there's a carbon sitting there, and on this side of the dashed line there's a hydrogen sitting there. Again, it's just a short form. When we go to draw these things, we're going to put in every single atom, so you don't have to worry about any of the short form stuff, and we're not going to worry about 3D. But I just want you to understand when you're looking at it, what you're looking at. Okay, so the point is, though, so we have all these functional groups all the way along here. And let me flip back to the other picture. And they have special names, and they're going to do special things, going to interact in special ways. So the first one that you're going to see all the time is going to be hydroxyl. This one's super important. I've put little stars here beside the 4 main ones that you really want to memorize. Move this out the way. Put that up there. So hydroxyl, carboxyl, amino, and phosphate. Memorize these ones. So the hydroxyl is the OH group that sticks off. You'll always see that popping off there. Carbonyl is a COH, but the C is double bonded to the oxygen, and then the H is coming off the C. Now you can have on the other side here, the reason I've got these dashed lines is because this is where they connect to the big molecule. So there's one more bond for carbon. It has 4 bonds, 1, 2, 3, 4, so it can attach to something here. Carbonyl, though, doesn't have to have the H. It can also just be a C to a double bond O, because I can rip that H off and then use this bond to stick it somewhere else. So you can find them all over the place, either on the end of a molecule like this, or in the middle of a molecule where you have something attached on this carbon, and then get rid of that H and have something else attached over here on the other side of the carbon. Carboxyl, super important one. Don't get carbonyl and carboxyl mixed up. Carboxyl is also double bonded to an O, but it has this OH group. This is not a hydroxyl. Hydroxyl is OH on its own, as its own little fancy dude. It'll do its own thing. This COOH is going to act as a full unit. So please don't think this is a carbonyl plus a carboxyl. It's not. A carbonyl plus a hydroxyl. It's not. This is its own thing. It'll be added and cut off as is. Okay. In fact, we're going to see this right through our unit. We'll keep talking about the carboxyls and as we go along with our discussion on photosynthesis and cellular respiration. Okay. Amino, another very important one. It's a nitrogen with a couple hydrogens attached, and here you can see there's an attachment to stick it to another molecule there. Sulfhydryl is when you have a sulfur attached to something, and usually it's attached on one side and has a hydrogen on the other. You can either draw it out like this, where you show the bond between the sulfur and the hydrogen, or you can write them nice and close together. Hydrogens are super tiny, and so they do tend to tuck into the other atoms. They get drawn pretty close. So we can simulate that by not showing the bond in between. But there is a bond. Just like up here on the hydroxyl, there is a bond, but you don't always have to show it. Right? Okay. Phosphate is the other one. Memorize phosphate. You'll see this over and over again right through our whole course. You have a phosphorus, and it's going to be double bonded up to the O, single bonded, single bonded, single bonded to all these other oxygens. And notice, though, that these oxygens are not satisfied by the phosphorus. In fact, there's too many bonds here. Phosphorus, if you look at it, scroll up here a little bit, it actually only has space for 3. So the fact that it's got 4 attached means that we were overloaded the phosphorus already. You've got some extra covalent bonds here. And that means that oxygen cannot be satisfied by the phosphorus because the phosphorus is sharing too many electrons with other atoms. So this is actually going to end up being a supercharged functional group that's going to help us to actually store a heck of a lot of energy. You'll see that as we talk about ATP and as we go forward from here. So you have your phosphorus. You have lots of space for these oxygens to be attached to something else. So very high energy phosphate group here. Okay. So now what I'd like you to do, go through on, I guess this is page 10 of your book, and just circle and list every single functional group that you can. Go ahead and do that. So you're going to be looking at your functional groups list on the note I just showed you there. I'll post it for you. And then circle and label as many as you possibly can. And we'll go from there. Okay. So I didn't do all of them here, but I would like you to just add in these carbons here. If you don't already know what this means, just add in the carbons just so you have an idea that there are carbons all over the place. And you can see here right on the end, you've got yourself an amino group and you've got a carbonyl sitting there. You can see that's actually quite a common thing to have an amino with a carbonyl next to it. It's quite common on this particular molecule. And then you can also see down here, you got yourself a phosphate group, and there are a few others in there as well. You can see there's a little hydroxyl here over on this side. Let me show you the other version because it's a little bit more detailed here. What I'd like you to do is circle this cobalt, if you haven't already, and label it as cobalt ion. And the idea would be that this giant vitamin B molecule does what we call chelating, C-H-E-L-E-A-T-S, chelates The CH makes a K sound. And basically it means that it surrounds this cobalt ion. If you didn't have the piece of cobalt in here, this would not function as a vitamin B. It wouldn't work. And vitamin B is supposed to help with chemical reactions and all sorts of stuff. Okay, so you can see there's carbons all over the place. You got little hydrogens sticking off into nowhere land. You've got the darker, thick ones coming towards you and the dashed ones heading away from you, and so on and so forth, and all the different functional groups there. Okay, so hopefully you had a chance to look at that. This will be posted, so you'll be able to see this. These are the major topics that I want to try to briefly go through with you. First of all, intra versus intermolecular forces. This is intramolecular, is the force that holds this big molecule together. So any of these bonds that are kind of holding the thing together, those are intramolecular forces. Intermolecular forces are when one molecule is attracted to another. So that's what holds them together. When they're not the same molecule, it's two different. So intra, within the molecule holding it together, and then inter is holding two molecules together. Electronegativity is how much it loves its electrons and how negative it can get. The ionic bonds versus covalent bonds will go over. Polar covalent we're about to go over. Nonpolar will go over. Hydrogen bond will go over. Hydrophobic, hydrophilic. Hopefully you've seen this word phobia before. Phobia means fear if you don't know your Greek. And so if you're hydrophobic, you have a fear of water. This one's a little less known, this philic word. Philic refers to one of the three major types of love in Greek philosophy. So you have your agape love, which would be this perfect, wonderful, unconditional love, like the love of God for his creation or the mother for their child, this agape love. Then you get the eros love, and that's the romantic version of love. And then you get just the friendly brotherly love, and that's what philia is. Philia is brotherly love. So if you're hydrophilic, you like water. If you're hydrophobic, you try to stay away from it. You have a fear of it or you have a love for it. Right? Ions, hopefully you already know that's just regular atoms that have either gained or lost electrons, so they're no longer neutral. And then you did some reactions in grade 10. Neutralization was one of them. That's when you put an acid and a base together and you always get out some kind of a salt, which is the leftover stuff, and water. Buffer we'll talk about more as we go along. That just helps you with your acid-base levels, your pH levels. Oxidation and reduction we'll go over a million times. A redox reaction is just using oxidation and reduction. Oxidation just basically means you have lost an electron. So we have these little acronyms that sometimes chemistry teachers will use. LEOGR, so losing electrons is oxidation. Gaining electrons is reduction. LEOGR. Or you can use the other one, oil rig. Oxidation is losing. Reduction is gaining. So oxidation, you've lost an electron. Reduction, you've got an extra one now. Or you've gained one. Okay, we'll talk about that lots. A redox reaction is when one thing becomes oxidized because it gives its electron to something else. That's a redox reaction. Reduction, oxidation. Condensation and hydrolysis, you'll see that as we go along. So I'm not going to talk about that now. I'll talk about that when we talk about carbs after. So ionic bonding, ionic versus covalent. And again, this is going back to grade 9 and 10, but it's important for you to understand how we're building our molecules. So I want to, and how they interact with each other. So both the intramolecular, within, and intermolecular, between the molecules. So it's going to matter. So ionic bonding is basically when you've got two different atoms, one that has a very low affinity or low love of electron, and one that has a very high affinity or a high electronegativity. Something with a high affinity or high electronegativity would be your nonmetals, so your oxygens, your fluorines, your nitrogens, and so on, phosphorus, sulfur. Low affinity atoms tend to be things like metals, plus poor little hydrogen. Hydrogen, the wuss of the atomic world. It only has a proton and one electron. So it's very difficult if a larger atom comes along for poor little hydrogen to hang on to its electron. Just too little, poor little guy. So the electrons then, because one guy loves electrons more than the other, you're going to see those electrons get transferred from the low affinity atom, which means it'll form something called a cation, to be positively charged, and then the high affinity atom gets the electron, so it becomes negatively charged, like an anion. When I'm teaching this to my grade 9s and 10s, I always tell them, if you want to remember which one's positive and which one's negative, the positive one, if you look at the word cation, the T sort of looks like a plus sign. Look at it that way if you want. Anion, I always think this looks like the word onion. Onions make you cry. Crying is a negative experience, therefore anions are negative. So however you remember it, it's up to you. But kind of stick that into your arsenal of things that you know that you can pull out at the next family dinner and impress grandma. Okay? So ionic bonding, you have a transfer of electrons. Okay? So then in other words, the sodium, when it loses its one electron and gives it up to the chlorine, it becomes what we call oxidized. It is now, you can see over here on the right-hand side, it's now a positively charged ion. And by one plus, because it lost one electron. When the chlorine gained that electron, it became reduced. It gained one electron, so it has a charge of -1. And now, because both of these ions are charged, oppositely charged, they can be attracted to one another. It only takes one sodium to satisfy one chlorine, and you get yourself something called an ionic crystal. It's not really quite a compound. It's more of an ionic crystal, but I guess it's a compound. It's not a molecule. It's a compound that is an ionic crystal, but that's probably beyond the scope of this course. So you get sodium, chlorine. When they have these inter forces between them, they get attracted and they form an intra bond. Okay, it's actually a pretty weak bond. You can take sodium chloride, which is basically table salt. You can throw it into water, and it'll fall apart into its ions. So the ions, we say, would dissociate or separate in water. So even water is able to separate these little bonds and make them kind of pop off each other. But as soon as you remove the water, they go back to clicking in together. Right? So that's ionic bonding. You transfer one to the other. One becomes oxidized, the other becomes reduced, and you get yourself an ionic crystal out of that. When you're talking about covalent bonding happens between atoms where they both have high electronegativity. So in other words, nobody wants to give up an electron. They love their electrons, but they are willing to share them and basically give temporary custody to these electrons. Right? So you don't actually get any ions created, none whatsoever. Nothing becomes positive, nothing becomes negative overall. They get shared. So if we look back again at carbon has 4 available bonding sites. Hydrogen has 1. So that means I could click a hydrogen into every single spot here. And in fact, I do that, and I get myself a methane, a CH4 group. And I've color-coded it here for you so you can see the difference. But again, the iPad sometimes erases a little bit. There's supposed to be a red dot there. Now, you can draw it as the Lewis dot structure if you want, or you can know the rules where every time you have a shared pair, you can replace those 2 dots with 1 line. So we replace the dots with 1 line, replace the dots with 1 line. And these are the structures that we're going to end up drawing. We're not going to worry about dots. We're just going to draw. And you can see here that because every line represents 2 electrons, these 2 electrons now are going to spend some time around hydrogen, these 2 around that hydrogen, these 2 around that hydrogen. So the hydrogen is going to be neutral. It's going to be nice and happy and have all neutral and stable. Stable meaning that it's got a full outer shell. And then carbon has space for 8, so it's going to be stable as well. So this is a nice, happy molecule. Everybody's sort of sharing equally. And so all these electrons spend some time around carbon and some time around each of the hydrogens. Shared, that's the key. Covalent. Valent is the name of the outside shell. So these electrons are in the valence shells for both of these atoms. And co means to share, so I'm sharing the outside. All right. So again, I know it's grade 10. Some of you guys are like, oh, I've already done 12U. Why are we talking about this? Because there's some people that haven't done it since grade 10. It's been a while. So I just want to be kind to everybody. Okay, so that's a covalent bond. Sometimes, though, you get a greedy hog like oxygen. Technically, it's a nonmetal with a nonmetal. Technically, this electron, when donated to the to the oxygen, should also, if you look down here, these 2 electrons here on the left-hand side should both spend some time around the hydrogen, satisfying it and making it stable. And they should also spend some time around the oxygen and make it stable. But the reality is that the oxygen, although technically this is a covalent bond, technically they are sharing, the oxygen is the godfather. So it's basically like ripping lunch money off of this poor little pathetic hydrogen. Poor little wuss of the atomic world can't hang on to that electron very well. So that what actually ends up happening is, even though this is how you would draw your molecule, so yeah, there's a covalent bond there, those electrons that should spend time around hydrogen actually spend more of their time around the greedy hog of oxygen, the greedy electron hog. So because they're spending more time around here, it means that most of the time, the oxygen at the bottom is ever so slightly negative. This little weird squiggly symbol is the Greek lowercase d. It's called delta. And when we're using it in this context, it just means slightly. So because we have these electrons, even though this is a shared pair, most of the time these electrons will be whizzing around the oxygen, making it ever so slightly negative. And because hydrogen then is sometimes missing those electrons, it's ever so slightly positive. Not enough to say that these are ions. This is still covalent. They're still technically sharing. It's just basically like this guy gets more time. It's got a greater share of the custody than these little hydrogens here. Okay? So if you want to think of it in those terms, that would be great. This explains a lot of things as we move forward, this idea of a covalent bond that is not equal. And we call this polar covalent. Polar covalent. So yeah, covalent, you're sharing the electrons, but polar means you've got opposite charges on these molecules. So you can see you've got a positive end, and then you've got yourself a negative end down here. So covalent versus ionic, hopefully that's good. So we've got ionic, electrons being transferred, so you actually get ions. Something gets oxidized, something gets reduced, and then they can have this loose connection. It's a weak bond. Covalent bonds are actually pretty strong. Much, much, much stronger than this weak little ionic bond. So whereas ions can dissolve in water, they can separate and dissolve in water, covalent bonds can't be broken up by water. So you'll find that when you throw something that is covalent into water, it stays as its own container. It doesn't fall apart. And this is one of the reasons why you can look at the idea that oil and water don't mix. Oil is a non-polar molecule, but water is a polar molecule. So we'll talk about that as well when we talk about dissolving in a second here, but let me finish this conversation off first. So the idea that water has this slightly polar nature to it, slightly positive hydrogen, slightly negative oxygens, explains why it is that when water freezes, it actually expands. According to particle theory, you learned this in elementary school, we covered it again in grade 9, probably briefly touched on it in grade 10. According to particle theory, everything is made of particles. These particles are attracted to one another. There is space between them, and you can combine them to form molecules. That's the basic particle theory kind of an idea. So there is space between all of these molecules. But the other part is that if you begin to remove energy, in other words, you begin to cool something down. So you start off with a gas, and you begin to cool that gas down, then these particles are going to get closer and closer and closer to one another. When they get close enough, they will form a liquid, so they'll change state. And if they get even closer to one another, they should form a solid. So you should expect then that in a regular, just a normal, like let's say metal, you can have a metal can be in all different phases or states of matter as well. So let's say you have metal as a gas. It would have to be really hot for it to be a gas. But let's say it's as a gas. Then you can cool it down into molten metal, and now it's a liquid. And then you can allow it to cool again into a solid. And if you keep cooling that solid metal, it'll keep getting smaller and smaller. It'll contract and contract and contract. This is actually a good way if you've got a jar stuck, like you're trying to open the pickle jar, and you've already banged it and you've already tried to really grip it. Go throw that pickle jar underneath hot water, just the lid, the metal lid. The metal lid, when it warms up, will expand ever so slightly. Not enough heat for it to become a liquid, but enough heat for it to become a less dense solid. When it expands a little bit, it'll be easier to open the pickle jar, and away you go. So normally, when things go from liquid to solid, or just from solid to even colder solids, you should see them contract. They should shrink because there's less and less space between the molecules. But when you throw water into the freezer, or if you're unlucky and you left a case of pop in your car, you'll find out very quickly that when you freeze it, it doesn't shrink, it actually expands. And the reason for that is because of this polar covalent nature of the water. As these molecules get closer and closer and closer together, rather than them just sitting close, because you've got this oxygen that's ever so slightly negative and these hydrogens that are ever so slightly positive, the negative oxygens will push away from each other, and the oppositely charged oxygen and hydrogen will pull together. So you end up with these, like a crystal shape that ends up happening. That's why water forms these solid crystals, crystallizes. And so then what we actually end up what actually ends up happening then is we get the space in between, and the solid water will actually expand. And there's now space in between those molecules locked into place because of this attraction, this intermolecular attraction between two molecules based on their polarity. Okay, so that explains why water is going to actually expand rather than contract like a regular solid would. Okay, and remember, we've got our terms as we're going from a gas to a liquid. We can say it condenses into a liquid, contracts and gets closer, and then when it freezes into a solid, it should condense even further. It should get closer and closer together. But again, because of the polar nature, it'll actually push apart and lock into this crystal structure with these nice defined spaces in between. Okay, the idea of this hydrogen right here being attracted to this negative oxygen, there's no actual bond formed here. There is an attraction formed. Unfortunately, we use the word bond though. This idea here of this slightly positive area of a molecule and a slightly negative area of another molecule being attracted to one another is called a hydrogen bond when hydrogen is involved. Again, not a real bond. I'm not sharing electrons. I just have a very weak attraction holding this together. It only takes a little bit of energy, a little bit of heat to knock these apart and turn it back into a liquid. But that's what's going to happen in between there. So hydrogen bonding, it's going to explain so much about how proteins fold, about how your DNA sticks together. All these kinds of things are going to be explained by hydrogen bonds. So it's important that you get this idea of polar covalent down right at the very beginning. Okay? Hydrogen bonds. So another thing you're going to see then is the interaction between different types of molecules. We have this saying in chemistry, like dissolves like. And basically what it means is that if you have a polar molecule, so not water itself, but just anything that's polar, so that would be the solute, and you try to dissolve it in the water, you throw it into water, it will dissolve. You will actually see, this is like the NaCl, the salt above being thrown in or something like that. Something small that's polar, when you throw it into water, it will dissolve, okay? And we would say that like dissolves like. So polar molecules dissolve in polar solvents like water. Nonpolar dissolves in nonpolar. So if you're thinking about this then, oil would be considered a nonpolar molecule. You'll see that as we discuss this later when we really get into talking about the structure of these things later today. So oil, being nonpolar, does not dissolve in water. It won't mix, but obviously water is polar. So when we have polar with polar, we can dissolve it. When we have nonpolar with nonpolar, we can dissolve it. But when you mix them, nonpolar with a polar thing, you cannot dissolve it. So then we bring in these terms hydrophobic and hydrophilic. Okay? Remember, this is pertaining to water. Philic, you love water. Phobic, you have a fear of water. So if you are a polar molecule, you are considered hydrophilic, you will dissolve. If it's a nonpolar molecule, it's considered hydrophobic, it will not dissolve. And these are key little concepts that you kind of need to pick up as we go along. Briefly mentioning them here, and then I'm going to show you how they apply as we go along. But really, you need to know the idea of hydrogen bonds. You need to know polar versus nonpolar, what that means. And again, that's whether it's sharing electrons equally or not. And the idea of hydrophilic and hydrophobic. If you can tuck those terms away today, you're going to be doing well for this before lunch session.